Uh, the way we go about the physiology of the adrenal gland, we are going to talk about uh, the synthesis of the different hormones in the adrenal gland. We are going to talk about the regulation, and then we are going to talk about the functions of the hormones. So, every time you are going to read any endocrine gland, we are going to talk about the synthesis, the regulation, actions of the hormones, and then we are going to relate it with pathophysiology of disease. If there is a hyper secretion of the hormone or hyposecretion of the hormone, what are the effects or what type of diseases you are going to see. And usually when we are testing the physiology or the functions of these hormones, we use the pathophysiology to test your knowledge of function of these hormones. So it is very important that when you are looking at the actions of the hormones, you always think about what would happen if there is hypersecretion, what would happen if there is hyposecretion, what can go wrong in the synthesis of the hormone, what can go wrong in terms of regulation of the hormones. So this is how you always think or try to read the endocrine physiology. Okay? So if you do that, it would be easy. But if you just keep on trying to remember the actions of the hormones or the steps of synthesis, it would not help you in the exam. In the exam, most of the questions would be based on what can go wrong in the synthesis, what can go wrong in the regulation, what can happen because of hyper and hyposecretion. We're just testing indirectly the actions of the hormones. Okay? So we'll start with the adrenal gland today. We know that adrenal glands are paired pyramidal glands shaped organs on the top of the kidneys. They weigh around 6 to 10 grams. Structurally and functionally, they are two glands in one, because the adrenal cortex is a glandular tissue which is derived from the embryonic mesoderm, we know that, and forms about 80 to 90% of the gland. And adrenal medulla is formed from the neural ectoderm, and it is mainly a modified sympathetic ganglion. Okay? So it's a modified sympathetic ganglion. It's part of the sympathetic nervous system, and it is going to secrete more epinephrine than epinephrine. It forms about 10 to 20% of the gland. If you, by weight, look at the adrenal gland, it is probably the richest organ which is supplied by blood. So it is, in terms of weight of the organ, it is the highest, it is supplied by the blood in terms of the highest volume of blood is being supplied to the adrenal gland in terms of weight of the gland. Okay? So synthesize, adrenal cortex synthesizes three set of hormones. There are three corticosteroids produced in each of the three layers. We know that zona glomerulosa produces adrenocorticoids, which is called mainly the aldosterone. Zona fasciculata produces glucocorticoids and some amount of androgens. Mainly cortisol and corticosterone are the major steroids or glucocorticoids which are produced by zona fasciculata. Zona reticularis mainly produce gonadocorticoids, which are androgens, mainly dehydroepiandrosterone, which is DHEA, is the main androgen which is being produced by zona reticularis. The biggest layer within the adrenal cortex is the zona fasciculata, which forms about 70 to 80% of the cortex. Then you have zona glomerulosa, which is 15 to 20%, and zona reticularis is about 7%. The androgens have a major role in females because they are male hormones mainly, which are produced by the zona reticularis. So in females, because you don't have male hormones, so these are, or the androgens, they are the only source of androgens which are present in females. In males, because you have testes and you produce testosterone, which is the main hormone, and these androgens will go also to testes where they will be converted into testosterone. So the androgens have very little role in males, but androgens have an important role in female because they are the only source of male hormones in female. Now you can see the layers. You have the capsule, then you have zona glomerulosa, which produces the aldosterone, and you have zona fasciculata, which mainly produce, glucocorticoids, and glucocorticoids among them, the major one is cortisol, and then you have corticosterone, which is the other one. It also produces some amount of androgen. Zona reticularis is mainly a layer which is going to produce the androgens, and among them is DHEA, which is the dihydroandrosterone, which is basically the main androgen produced by the zona reticularis. Adrenal medulla, we know that it's a modified sympathetic ganglion, which is going to produce norepinephrine and epinephrine in response to the acetylcholine, which is coming in as a preganglionic neurotransmitter. So this will cause release of norepinephrine and epinephrine. If we look at a little bit of the hypothalamic pituitary axis, we know that there is a diurnal rhythm. That means there are changes in release of hormones from the hypothalamus based on day and night cycle. So because of the changes in the day and night cycle, you would have certain hormones released at a diurnal or pulsatile rate from the hypothalamus. One of them is the CRH, which is the corticotropic releasing hormone. We also have actions like, from the limbic system, like physical, emotional, and biochemical, which also affect this nucleus in the hypothalamus, which is the paraventricular nucleus. And this paraventricular nucleus releases the CRH, which is the corticotropic releasing hormone, into the median eminence, from where it is taken through the long portal veins into the anterior pituitary. And in the anterior pituitary, you have corticotropes, which release the ACTH. And if you look at the corticotropes here, you can see the CRH is going to bind here, resulting in the cyclic AMP generation, and then you have the protein kinase A. This will cause the calcium channels to open, and the calcium is going to increase. Intracellular calcium will cause release of ACTH from corticotropes. And once the corticotropes are released, they are going to act on the adrenal cortex, and the adrenal cortex is going to, when the ACTH is going to bind to its receptors, again, you would have a cyclic AMP activity, which result in protein kinase A activation of P450, which are the cytochrome enzymes within the mitochondria, and synthesis of several enzymes in the steroid generating enzymes within the adrenal cortex. So the important thing which I wanted to refer is that once the ACTH is going to bind to its receptors on the adrenal cortical cells, it is going to increase the synthesis of steroid hormones. And it happens by movement of cholesterol into the mitochondria and generation of cytochrome P50 and the enzymes which are important for reduction. So what you need is ACTH to bind to the receptors on the adrenal cortical cells. Once it binds there, the generation of cyclic AMP and pKa will result in induction of the cytochrome P50 system. So cholesterol moves into the mitochondria, and when the cholesterol moves into the mitochondria, there would be oxidation and reduction reactions which will generate steroid hormones. So for understanding the synthesis of these steroid hormones, we need to understand the structure of cholesterol, and we need to understand some important points in terms of the structure of these hormones, because the enzymes which are acting on the cholesterol are basically chopping up some side chains, adding hydroxyl group, adding an oxygen group. So you can remember even the name of enzymes just by understanding the structure of these hormones. So the first thing which you need to understand is that cholesterol is a 21 carbon compound, and it has 4 rings, A, B, C, D. So this is up to here 18 carbons. Then you have the 20 and 21 carbon, and then it also has some side chains. So it has a 21 carbon compound, and it also has some side chains. Now if you look at the cortisol and aldosterone, both are 21 carbon compounds. So you can see that it has both of them have 4 rings, and they are 21 carbon compounds, but they do not have these side chains. In terms of the estradiol, you would see that this is an 18 carbon compound. So it doesn't have the 21 carbon, 20 and 21 carbons which are stationed here. What you are finding here in the estradiol or estrogen, it's an 18 carbon compound. So all steroids of the adrenal cortex are chemical modifications of the basic steroid nucleus, which is illustrated in the structure of the cholesterol. The basic nucleus has a skeleton with carbons number 1 through 21 and 4 labeled rings, which are A, B, C, and D. The glucocorticoids, which are represented by cortisol, have a ketone group at carbon 3 and hydroxyl group at carbon 11 and 21. So if you see here, let me show you. This is the 21 carbon compound. So you can see the labeling of all the carbon atoms. And then you can see the cortisol has a ketone group at carbon 3, and it has a hydroxyl group at carbon 11. This is the carbon 11, and has a hydroxyl group at carbon 21. So it has 2 hydroxyl groups, one at carbon 11 and one at carbon 21, and a ketone group at carbon 3. This is cortisol. So if you look at the cholesterol structure and you look at the cortisol structure, first thing is that there are no side chains. So these side chains are gone. The other thing is that you have hydroxyl group at carbon 11, hydroxyl group at carbon 21, and a ketone group at carbon 3. If we look at the mineralocorticoid, like aldosterone, they have a double bond oxygen at carbon 18. So if we see here, aldosterone has a double bond oxygen group at carbon 18. So they have a double bond at carbon 3, and they have a double bond oxygen at carbon 18. But this double bond at carbon 3 or ketone group is similar to cortisol. But this is different, that at carbon 18 you have a double bond oxygen which is present in aldosterone. That differentiates it from cortisol. The rest of the structure you see almost identical. If you see the structure of the main androsterone, androgens, which are the dehydroepiandrosterone, which is DHEA, or androstenedione, they have a double bond oxygen at carbon 17, and they do not have carbon 20 and 21 side chain. So if you see here, you don't have any 20 and 21 carbon here in these two compounds, and you have a double bond oxygen at carbon 17. Here you have double bond oxygen at carbon 18. Here you are having double bond oxygen at carbon 18. And you do not have in the androgens the side chains. The carbon 20 and carbon 21 side chain are no more there. So they are mainly an 18 carbon compound. So DHEA and androstenedione are basically 18 carbon carbon compounds or steroids. So steroids are derived from cholesterol, and cholesterol is from the lipid droplets in the cortical cell. They enter as cholesterol esters in LDL. Removed cholesterol is replenished by cholesterol in the LDL in the blood or synthesized from the acetate. Steroid hormones are synthesized and they are secreted, not stored. So you have no storage of steroid hormone. When you have ACTH, you start synthesis of these steroid hormones. The first step in the steroid hormone synthesis is the rate limiting step, which is the cholesterol demolase. The cholesterol demolase enzyme, which chops off the side chains from the cholesterol. You have after carbon 21, there are side chains. So cholesterol demolase actually removes the side chains of cholesterol. So cholesterol demolase is the first step in the synthesis of steroid hormones. So when ACTH is going to come in, bind to ACTH receptor, it will induce the enzyme production of cholesterol demolase, and cholesterol demolase is going to chop off the side chains from the cholesterol, converting the cholesterol to pregnenolone. So from cholesterol, you have pregnenolone formed, and this is under the action of cholesterol demolase. So conversion of cholesterol to pregnenolone by enzyme cholesterol dismolase, cholesterol side chain cleavage enzyme. So this cholesterol demolase is the rate limiting step in the generation of the steroid hormone. So newly synthesized steroid hormones are rapidly secreted from the cell, and following the secretion, all steroid hormones are going to bind to plasma proteins. So they are going to bind to cholesterol binding globulin and albumin. So let's look at the cortisol synthesis, then we are going to look at the mineralocorticoid synthesis, and then we are going to look at the androgen synthesis. So the major glucocorticoid produced in humans is cortisol, which is hydrocortisol. This is synthesized mainly in zona fasciculata and reticularis. So in certain layers there would be deficiency of certain enzymes, and that's why you are going to produce certain set of hormones within a certain layer of adrenal cortex. So zona glomerulosa is only going to produce mineralocorticoid because it would have a deficiency of an enzyme which is not allowing it to produce cortisol or corticosterone, okay? And similarly, androgens. And similarly to the zona fasciculata, it might have a deficiency of an enzyme which will not allow it to produce aldosterone. So these are the deficiency of certain enzymes will restrict the formation of certain hormones to a particular layer within the adrenal cortex. So in the zona fasciculata and reticularis, cortisol is formed, which is the major glucocorticoid. Zona fasciculata thus contains all the enzymes required to convert the cholesterol to cortisol. So the first step is cortisol desmolase, which converts the cortisol into pregnenolone, and then you need an enzyme which is called 17-alpha hydroxylase, and this 17-alpha hydroxylase converts or hydroxylates pregnenolone to 17-hydroxypregnenolone. So once you have pregnenolone formed from cholesterol, then you need an enzyme which is called 17-alpha hydroxylase, which converts pregnenolone to 17-hydroxypregnenolone, or it may also convert it into progesterone. Once you have 17-hydroxypregnenolone formed, 3-beta hydroxysteroid dehydrogenases converts 17-hydroxypregnenolone to 17-hydroxyprogesterone. And once you have 17-hydroxyprogesterone formed, then you need two enzymes. One is 21-beta, which removes hydroxyl group from the 21 hydroxylase which add hydroxyl group at 21 carbon, and the other one is the 11 beta hydroxylase which add hydroxyl group at 11 carbon. So these two enzymes are going to convert the 17 hydroxyprogesterone into cortisol. So first 21 beta, and then you have 11 beta hydroxylase. So let's see here. So this is the cholesterol. You have the cholesterol desmolase, which is under the action of ACTH. So this is a rate limiting enzyme. From cholesterol, under the action of cholesterol desmolase, you have produced the pregnenolone. And pregnenolone is converted by the 17 alpha hydroxylase into 17 hydroxy pregnenolone. Then what happens is that 3 beta hydroxysteroid is going to convert pregnenolone to progesterone, and 17 hydroxy pregnenolone to 17 hydroxy progesterone. So 3 beta hydroxy steroid dehydrogenase is important because it is converting the 7 hydroxy pregnenolone to 17 hydroxy progesterone. Then you are adding hydroxyl group to 21 carbon atom, so you need a 21 beta hydroxylase which converts it into 11 deoxycortisol, and then you have 11 beta hydroxylates which add a hydroxyl group to 11 carbon position. This will result in the formation of cortisol. Now you can also have corticosterone form, and corticosterone is formed from pregnenolone to progesterone, and from progesterone you have 11 deoxycorticosterone and corticosterone under the action of 21 beta hydroxylase and 11 beta hydroxylase. You do not have aldosterone synthetase in the zona fasciculata and reticularis. That's why you cannot convert corticosterone into aldosterone. So you do not produce aldosterone in the zona fasciculata because you do not have this enzyme, which is the aldosterone synthetase. So you can produce corticosterone, you can produce cortisol in the zona fasciculata. The major enzymes which you need are desmolase, which is there, which is the main rate limiting enzyme. You need 3 beta hydroxylate, you need 21 beta hydroxylase, and you need 11 beta hydroxylase. If you have deficiency of all these enzymes, the corticosterone and cortisol would not be produced. And what would happen because of that? You cannot survive. So for life you need both cortisone and corticosterol or glucocorticoid, and for that you need these 3 enzymes as well as the cholesterol desmolase. You might have a deficiency of 17 hydroxylase, but that deficiency will not cause stopping of the production of corticosterone. You still would be able, if you have deficiency of 17 alpha hydroxylase, you still would be able to produce corticosterone. You would not be able to produce cortisol. You also need to understand that if you have deficiency of these hormones like 21 beta hydroxylase or 11 beta hydroxylase, this cycle is going to shift towards this side. Okay, this means that you start to produce more of androgens. If you do not have 17 alpha hydroxylase, this cycle is going to shift towards this side. That means you start to produce more cortisol and more aldosterone. So if you have deficiency of 17 alpha hydroxylase, this cycle is going to shift to this side. More of cortisol, more of aldosterone. If you have deficiency of 17 alpha hydroxylase, this synthesis is going to shift to this side. More of androgens would be produced. So if you think, you would understand that the actions, if you have the deficiency of these hormones, you would have more androgenic effect in females. because you have more androgens produced. Males would not have more effect because they already produce testosterone. But if you have more of androgenic hormones produced, you would have hirsutism, virilization within females because you are producing more androgens. If you are not producing 17 alpha hydroxylase, this cycle is going to shift towards this side, meaning that you would have more mineralocorticoid activity and you would have more glucocorticoid activity. So you need to think and look at the deficiency of enzymes and think what can happen. Okay? So cortisol is not the only steroid in the pathway with the glucocorticoid activity. Corticosterone is also a glucocorticoid. So we showed you that cortisol as well as corticosterone both are glucocorticoids. So the cortisol is not the only steroid hormone with the glucocorticoid activity. The 17 alpha hydroxylase step, if it is blocked, the zona fasciculata still can produce corticosterone without deleterious effect. So if we go back, you see if we block this, you can still produce corticosterone because pregnenolone can be converted to progesterone and progesterone can be converted to 11-deoxycorticosterone and then corticosterone. So this activity still can go on even if you have inhibition of the blockage of the 17 alpha hydroxylase, because this is going to produce still the corticosterone. So, and the blocks at the cholesterol desmolase, 3-beta hydroxysteroid dehydrogenase, 21-beta hydroxylase or 11-beta hydroxylase steps are devastating because they can prevent the production of cortisol and corticosterone. So if you have blocks here, or you have a block here, or you have a block here, or you have a block here, these 4 enzymes, if you block, you cannot produce corticosterone or you cannot produce the cortisol. So blocks of cholesterol desmolase, 3-beta hydroxysteroid dehydrogenase, 21-beta hydroxylase and 11-beta hydroxylase will stop the production of corticosteroid and cortisol. So this will be devastating and this will lead to death if you are not going to replace the steroid hormones. Metyrocone and ketoconazole are drugs which inhibit the glucocorticoid biosynthesis. Metyrocone inhibits the 11-beta hydroxylase, which is the last step in the production of cortisol or corticosterone. So metyrocone is only going to inhibit the 11-beta hydroxylase, which is the last step of converting the 11, if you go back, you can see that this 11-beta hydroxylase is converting 11-deoxycortisol or 11-deoxycorticosterone into cortisol or corticosterone respectively. So if you block this, you are not able to synthesize either cortisol or corticosterone. Ketoconazole can inhibit several steps in the pathway, so it is not targeting one particular piece, but it can inhibit several steps, including the rate-limiting enzyme, which is the cholesterol desmolase. So ketoconazole and metyrocone are the 2 drugs which can inhibit the synthesis of glucocorticoids. Now we are coming to the androgen synthesis. We know that there are 2 androgens. One is the DHEA and the other is the androstenedione. They have androgenic steroids produced by zona fasciculata and reticularis. These compounds have weak androgenic activity, but in testes they are converted to testosterone, which is a more potent androgen. So that's why the effect of adrenal androgens in males are not very visible, because you already have a hormone which is testosterone, and they are going to be converted into testosterone within the testes. But in females, if you have high levels of androgens, it is going to cause hirsutism, it will cause virilization of their secondary sexual characters because of high levels of androgens. The precursor of the adrenal androgen is 17-hydroxypregnenolone or 17-hydroxyprogesterone, which is produced by 17-hydroxylase, beta-hydroxylase from pregnenolone or from progesterone. So from pregnenolone or pregnenolone, if the enzyme 17-beta-hydroxylase is going to act, it is going to produce 17-hydroxyprogesterone or 17-hydroxypregnenolone. Now, if you remember, androgens do not have carbon 20 and 21. So you need another enzyme which is going to remove the carbon 20 and 21, and that would convert the progesterone or 17-hydroxyprogesterone or 17-hydroxypregnenolone into DHEA or androstenedione. So if we look at the structure here, you need an enzyme which is the 17-alpha-hydroxylase, which is converting the pregnenolone to 17-hydroxypregnenolone, and you need this enzyme to convert the progesterone to 17-hydroxyprogesterone. And then you need this lyase, which is 17-20 lyase, which is removing the carbon 20 and 21 from the progesterone, 17-hydroxyprogesterone and 17-hydroxypregnenolone, converting them into dehydroepiandrosterone or androstenedione respectively. You can also convert dehydroepiandrosterone by 3-beta-hydroxystenoid dehydrogenase to androstenedione, but both of them are basically androgens, and they are converted within the testes into testosterone, and into the liver can be converted into the estradiol. But what you need to understand is that you need 17-alpha-hydroxylase, which will convert either pregnenolone or progesterone into 17-hydroxypregnenolone or 17-hydroxyprogesterone, and then you need to chop off the carbon 20 and 21, which is done by the 17-20 lyase, and it is going to remove these carbons, converting them into DHEA and androstenedione. Now, in males, androgens are of little significance because they are produced by the testes. In females, however, adrenal cortex is the major source of androgenic compounds. So if you have a blockage of 21-beta-hydroxylase or 11-beta-hydroxylase, which are important in the cortisol synthesis, then cortisol will not be formed. And what would happen? It would shift towards becoming, more of androgens. So enzyme deficiencies like 21-beta-hydroxylase or enzyme deficiency in terms of 11-beta-hydroxylase, which are main enzymes in the cortisol or corticosteroid or mineralocorticoid pathway, will result in more of androgen production, and this androgen production is going to show off mainly in females with hirsutism and virilization. On the other hand, if you have deficiency of 17-alpha-hydroxylase, this will shift the cycle towards more of the glucocorticoid production and mineralocorticoid production. So you start to have more features of overactivity of mineralocorticoids as well as steroids. So you need to keep thinking about the synthesis and see where the deficiency of the enzymes are. This is the favorite question, although these diseases are not that common, but board exams test the synthesis of androgens by using the enzyme deficiencies. So they will keep on asking you, deficiency of 21-beta-hydroxylase, deficiency of 11-beta-hydroxylase, deficiency of 17-alpha-hydroxylase. Those three enzyme deficiencies you would keep on being asked, because the only enzyme, the other enzyme which is rate limiting in the synthesis is cholesterol desmolase. The rest of it, the three enzymes where the deficiencies would be, will result in either androgenic effect or more of corticosteroid and mineralocorticoid effects. They would be asked in terms of enzyme deficiency. So they are testing you if you really know the synthesis by just looking at asking you about enzyme deficiencies. So in terms of aldosterone synthesis, the major mineralocorticoid in the body is aldosterone, which is synthesized by zona glomerulosa, steps required to convert cholesterol to corticosterone are identical to those of zona fasciculata, and the addition of aldosterone synthetase in the zona glomerulosa converts the corticosterone to aldosterone. So until corticosteroid synthesis, the steps of production of aldosterone are similar, except that within the zona glomerulosa, you have aldosterone synthetase, which converts the corticosterone into aldosterone. So the zona glomerulosa does not produce glucocorticoids for two reasons. One is corticosterone, a glucocorticoid is converted to aldosterone because this zone contains aldosterone synthetase. The second thing is that zona glomerulosa lacks 17-alpha hydroxylase. So if you don't have 17-alpha hydroxylase, you cannot produce from pregnenolone 17-hydroxypregnenolone. You can only produce from pregnenolone progesterone. So you are producing from the pregnenolone progesterone, you are not producing 17-hydroxypregnenolone, which is important in the synthesis of cortisol, but it is not important in the synthesis of corticosterone. So these are the two reasons why zona glomerulosa does not produce glucocorticoid, because all corticosterone which is produced here is converted into aldosterone by the action of aldosterone synthetase, while it does not have 17-alpha hydroxylase, so it is not producing 17-hydroxypregnenolone, and then it is not producing 17-hydroxyprogesterone, and then it is not producing cortisol at all. That's why in zona glomerulosa, you are only going to produce aldosterone. Aldosterone is not only steroid which has the mineralocorticoid activity. So 11-deoxycorticosterone and corticosterone itself, they also have mineralocorticoid activity. So even if you do not have aldosterone synthetase, you are still going to produce corticosterone and 11-deoxycorticosterone. Both of them would have mineralocorticoid activity. The other thing which can happen, that if you have a block above the production of deoxycorticosterone, 11-deoxycorticosterone, then you would have no mineralocorticoid activity. So if you block there is absence of 11-beta hydroxylase or aldosterone synthesis, mineralocorticoid will still be able to be produced. But if the block is above, which is 21-beta hydroxylase, you cut off there, then you would have no mineralocorticoid activity, because you are not producing 11-beta corticosterone, as well as you are not basically producing corticosterone. So however, if the pathway is blocked above the level of DOC, that means the absence of 21-beta hydroxylase, then you have no mineralocorticoid activity. So if you see here, in this pathway, this 11-deoxycorticosterone, corticosterone, and aldosterone, all three of them have mineralocorticoid activity. So if you block this pathway above this, you have enzyme deficiency of 21-beta hydroxylase, or you have enzyme deficiency of D3-beta hydroxysteroid dehydrogenase, then you cannot produce any of the mineralocorticoids. All three of them have mineralocorticoid activity, but if you have a block here, you still are producing here. If you have a block here, you are not producing this, this, and this. So deficiency of 11-beta or deficiency of aldosterone synthetase still will produce 11-deoxycorticosterone, which has mineralocorticoid activity. But if you have deficiency of this, you are not producing this, this, or this, so you have no mineralocorticoid activity. Yes?
If it still has mineralocorticoid activity, how would we know this deficiency?
You check the enzyme levels.
For aldosterone?
Yes. Or you would start to, if you start to look at the levels of the intermediates. So if you have, for example, enzyme deficiency here, you would have high levels of 11-deoxycorticosterone. If you have enzyme deficiency here, you would have high levels of corticosterone. So you can check the enzyme deficiency without even looking at the enzyme by looking at the intermediates above them. If you have high levels of them, you know that there is enzyme deficiency below this. Okay? So there are three major enzyme deficiencies which the board exams are very interested in. One is the 17 hydroxylase deficiency. The other one is the 21 beta hydroxylase deficiency. And the third one is the 11 beta hydroxylase deficiency. So think about if you don't have 17 alpha hydroxylase, the cycle is going to shift towards your left. It's going to go this way. And it is going to create more corticosterone and it is going to create more aldosterone. So you would have more, and you would have less androgens. So there would be loss of pubic hair in females. There might be loss of axillary hair. They would have hypertension, hyperglycemia, because aldosterone is up, you would have more sodium, less potassium, and there would be pigmentation of the skin. All those things which are going to happen because of the activity of glucocorticoid as well as aldosterone. Imagine if you have deficiency of 21 beta hydroxylase. So you are not producing either cortisol and you are also not producing aldosterone. So you would have deficiency of glucocorticoids and you have deficiency of mineralocorticoids. So you would have hypoglycemia, you would have hypotension, you would have hyperkalemia, hyponatremia. So all those things are going to happen. Plus, because more androgens are going to be produced, so in females you would see hirsutism, you would start to see virilization of their sexual characters. The clitoris will become, will increase in size. So those type of features you are going to see with the 21 hydroxylase activity. Now, 11 beta hydroxylase deficiency will spare the the mineralocorticoid effect, the deficiency of mineralocorticoid, because you start to produce 11 deoxycorticosterone, which has a mineralocorticoid activity. The rest would be similar to 21 beta hydroxylase. So this is how you are going to look at the synthesis of the adrenal hormones. It's very important. It's very it is being tested a lot. So you need to concentrate on the synthesis of adrenal hormones. So you see here 17 alpha hydroxylase. If you would have deficiency of this enzyme, you would have more mineralocorticoid produced. You would have less cortisol produced, but corticosterone would be up. So sex hormones will be down, blood pressure would be up, potassium would be down, androstenedione, which is androgen, is going to be down. You would have an ambiguous genitalia in males with undescended testes if the child is born at the level of the child. In females, you would have lack of sexual development because pubic hair will not be there. There would be lack of sexual development, which is under the action of androgens. 21 beta hydroxylase, if it is deficient, you would have decreased mineralocorticoid and decreased cortisol. You would have increased sex hormones, decreased BP, increased potassium, increased renin activity, increased 17 hydroxyprogesterone, which is a precursor of the androgens, and you would have most common presents in infancy with salt wasting or childhood, precoccus puberty. In females, you would have hirsutism and virilization. In 11 beta hydroxylase, everything same is happening except you had to have increased activity of 11 deoxycortisone, which results in increase in blood pressure because you start to absorb salt and you would increase the extracellular fluid volume. Renin activity will go down, but you would have increased salt production, and you would also have decreased potassium because it has similar effects as aldosterone, and you would have virilization because the cycle is moving towards the right. Okay? Yes, go ahead.
Is deoxycorticosterone the one that's connected to aldosterone, or is
11-deoxycorticosterone, we said 11-deoxycorticosterone and corticosterone also have mineralocorticoid activity similar to aldosterone, both of them. So if you have 11-beta deficiency, you cannot convert 11-deoxycorticosterone into corticosterone, but you would still have 11-deoxycorticosterone, which has similar activity as aldosterone. So that's why you would not have salt losing effects of aldosterone, but you would have effects of corticosterol deficiency, and you would have deficiency of androgens. Clear? So these charts are there for you. You can keep on looking at it. It takes a little bit of time to get things in your head, but once you start to read them, it becomes easy. Okay? You understand, everybody? Any confusions, you can stop me here. But you should know this. This is a little bit complicated, but you should know this. This is going to be tested. Even in board exams, when you go in USMLEs, this is from first aid. They are going to test you on these. There are several questions on synthesis of adrenal hormones, and usually they are going to test you with the deficiencies of enzymes. Okay. So now we are coming to the regulation of the adrenocortical hormones. One more thing before I go to the regulation. You should also know that cortisol has more affinity to bind to mineralocorticoid receptors in the kidney. And you know that the levels of cortisol are much higher than aldosterone levels in the blood. So why cortisol don't bind to the mineralocorticoid receptors in the kidney and stop the action of mineralocorticoid? Because cortisol does not have mineralocorticoid activity, but it has more affinity to bind to the receptors of aldosterone in the kidney. So there is an enzyme within the kidney which converts cortisol into another product and which does not have an affinity to bind to the receptors of aldosterone. That's why you do not have, that's why the kidney can sense the actions of aldosterone, because it actually converts cortisol to another compound which has no affinity to or decreased affinity to bind to aldosterone receptors. But normally, if you see the cortisol and aldosterone, cortisol has more affinity to bind to aldosterone receptors as compared to aldosterone itself. But because kidneys, change it into another compound which does not have affinity to bind to the aldosterone receptors, it does not affect the kidneys, and aldosterone can affect the kidneys. Clear? Okay. So the synthesis of the regulation of the adrenocortical hormones, the synthesis and secretion of steroid hormones by the adrenal cortex depend on the stimulation of cholesterol desmolase, which is the first step in the synthesis of the steroid hormones, and this is under the action of ACTH. So when the ACTH is there, you would have cholesterol desmolase which is activated, and cholesterol desmolase is the first step and the rate limiting step in the synthesis of steroid hormones. And you know that steroid hormones are not stored, they are synthesized and released. So they are not like thyroid hormone, they are stored and then released as per demand. These are synthesized and released at the same time when the ACTH is going to come. So there are two questions. What regulates the secretion of ACTH, and what special regulatory factors control the function of the zona reticularis, fasciculata and glomerulosa? Zona fasciculata and reticularis is under exclusive control of hypothalamic pituitary axis, and the hypothalamic hormone is the CRH and the anterior pituitary hormone is ACTH. So you have CRH coming in from hypothalamus activating the ACTH, and ACTH is activating the adrenal cortex, the zona fasciculata and reticularis to release glucocorticoid as well as to release androgens. In terms of zona glomerulosa, although the first step of synthesis the cholesterol desmolase, is the same. So that is the only step which is ACTH has a little bit of role in release or synthesis of aldosterone, but the major control of synthesis of the aldosterone is mainly controlled by renin-angiotensin system. So the first step, which is the cholesterol desmolase, and the last step, which is the aldosterone synthetase, are basically under the control of ACTH. But the major control of zona glomerulosa is under the renin-angiotensin system. So zona fasciculata and reticularis are exclusively under the control of hypothalamic pituitary axis, which is CRH and ACTH. Here you have the first step, which is basically the synthesis of the cholesterol steroid hormones, which is cholesterol desmolase, is under the action of ACTH. The remaining part is mainly under the action of renin-angiotensin system. So mainly the aldosterone secretion is mainly under renin-angiotensin system, but it has a little bit of role from the ACTH secretion. Now we know that the cortisol secretion is it has a diurnal variation. That means in daytime and in nighttime it would have different types of concentration. So it is produced from the adrenal cortex or from the zona fasciculata and reticularis in a form of burst. So there are about 10 bursts or pulsatile bursts during 24 hours which release cortisol. Now the lowest amount is released near the midnight before you sleep, and the highest amount of cortisol is released in a burst just before awakening, around 8 o'clock. So around 8 o'clock you would have the highest amount of the burst of cortisol coming out, and around the midnight, in the night before you sleep, the cortisol levels are going down. So as the day progresses, your cortisol levels are going down. In the morning, your cortisol levels are up. So the other adrenal hormones like androgens and mineralocorticoids, they are also under the similar control or diurnal variation. ACTH secretion also exhibits the same diurnal pattern. In fact, it is the pattern of ACTH secretion which is controlling the secretion of cortisol. Okay, so ACTH secretion, if you look at it, it is going to mirror the secretion of cortisol. So if you see here, at noon time, this is the amount of cortisol. Just before sleep, you can see there is a dip, and just before awakening, there is a spike, which is the biggest spike which you see. That's why in the morning you feel fresh and you are ready to go, because you have high levels of cortisol, you have high levels of glucose in your system, so your energy is up. Negative feedback is exerted by cortisol at 3 levels. The first is that cortisol directly inhibits the secretion of CRH from hypothalamus. So cortisol is going back to the hypothalamus, decreasing the secretion of CRH. CRH decreases, it stops the secretion of ACTH. Second is cortisol indirectly inhibits the CRH secretion by the effect on hippocampal neurons. Hippocampal neurons are in the limbic system, and these neurons have projections into the hypothalamus. So cortisol is affecting hippocampus, hippocampus is affecting hypothalamus to decrease the secretion of the CRH. The third one is that cortisol is going to desensitize the receptors of CRH on the anterior pituitary. So now CRH cannot affect the anterior pituitary to release ACTH. So it is going to affect hypothalamus, it is going to affect the hippocampus, and hippocampus affecting the hypothalamus. And the third one, desensitization of the receptors of CRH on the anterior pituitary, thus decreasing the ACTH secretion. Thus, chronic deficiency of cortisol leads to stimulation of the CRH, ACTH, and increased ACTH levels are going to, this will result in increased ACTH level, and chronic excess of cortisol leads to inhibition of CRH, ACTH access and decreased ACTH levels. For example, chronic excess, like these bodybuilders and others, they put steroids to increase their muscle mass and other things. This is going to really stop. It will affect the ACTH and it will suppress the ACTH. So chronic taking of steroids will decrease the ACTH and it will ultimately result in adrenal atrophy. If you have low levels of ACTH for long period of time, it is going to result in atrophy of the adrenal cortex. So you need to understand the regulation here. So this is how it is happening. Adrenal cortex is releasing the cortisol. It is affecting the anterior pituitary and decreasing the effect of the CRH. It is directly affecting the hypothalamus, or it is going to affect the higher centers, which are going to affect the hypothalamus to release the CRH. Once CRH is released, it is going to activate the anterior pituitary. Anterior pituitary is going to release the ACTH, and ACTH is going to cause the production of the cortisol. Now we also know that from the anterior pituitary, the POMCs are going to release ACTH as well as MSH. So whenever you have hyperactivity of ACTH, you have increased levels of MSH also. So ACTH secretion will increase the cortisol secretion, but it will also secrete the MSH, which is going to cause pigmentation of the skin. So whenever you would have high levels of ACTH, you would have high levels of cortisol, and at the same time it can also result in pigmentation of skin. So these are the factors which stimulate the ACTH secretion. So one is the decreased blood cortisol levels. So if you have low cortisol level, your ACTH levels are going to increase. Your sleep-wake transition. If you change your sleep-wake transition, your cortisol levels are going to go down, and as a result, you would have more ACTH. For example, if you shift your sleep-wake cycling, like you keep awake for the whole night, your cortisol secretion is going to change also based on your sleep-wake cycle, and based on that, your ACTH, once your cortisol is going to go down, your ACTH is going to go up. You might also have stress, hypoglycemia, surgery. These are also the factors which are going to increase the ACTH, and as a result, you have increased cortisol secretion. So in stress, in surgery, in hypoglycemia, this is going to cause ACTH to be released, and ACTH is going to increase your cortisol secretion. So any type of stress, cortisol is a hormone which is going to be released in any type of stress, and usually it is because of ACTH. Stress, hypoglycemia, surgery, they are going to increase the ACTH secretion. As a result, cortisol is going to go up. Your psychological disturbances. So psychotic disturbances are going to affect the limbic system, and they are going to cause the CRH release from the hypothalamus and ultimately ACTH, and ultimately ACTH secretion is going to increase the cortisol secretion. ADH, antidiuretic hormone secretion, can also cause ACTH secretion to increase. Alpha adrenergic agonist, so those which are norepinephrine or epinephrine type of things are going to increase the ACTH secretion. Beta adrenergic antagonists are also going to cause the increase in the ACTH secretion, and serotonin. Release of serotonin can also cause increase in ACTH secretion. Inhibitory factors include increased blood cholesterol level, opioids, and somatostatin. So somatostatin, opioids, and increased cholesterol levels, cortisol levels are going to decrease the ACTH secretion. So these are the factors, you should know about them. In terms of the aldosterone secretion, so as we said, the aldosterone secretion is under the renin-angiotensin system. So when you have decreasing volume or pressure, the renin-angiotensin system will become activated. So when your blood volume to the kidney is low, or low GFR is there, renin is secreted, which is converted into angiotensin 1, and then ACE in the lung is going to change it into angiotensin 2. Angiotensin 2 is going to affect the adrenal cortex, and it is going to synthesize the aldosterone synthetase, which is going to convert the corticosterone into aldosterone, and this is going to cause the sodium absorption and potassium excretion and hydrogen excretion from the kidney, leading to hypernatremia, hypokalemia, and you would have alkalosis because you are releasing the hydrogen ion also in urine. So this is going to one of the mechanism is renin-angiotensin system. The other one, which is very important, is the potassium levels. So the adrenal cortex is very sensitive to potassium levels. So when you have high potassium levels and low sodium levels, so when you have high potassium levels, it is going to affect the adrenal cortex. It will depolarize the adrenal cortical cells or zona glomerulosa cells, releasing, increasing the intracellular calcium. And when you have increased intracellular calcium, it is going to release the aldosterone into the circulation. So potassium levels, high potassium levels are going to depolarize the zona glomerulosa cells. As a result, there would be influx of calcium, and increased intracellular calcium is going to release the aldosterone into the circulation. So the two important factors which are going to regulate the aldosterone secretion is the extracellular fluid volume, and the other one is the potassium, serum potassium levels. Sodium levels can also affect, and ACTH also has a role because it is important in the synthesis of cholesterol desmolase, but the major ones are this and this. So extracellular fluid volume and changes in the serum potassium levels are the major control mechanisms of aldosterone secretion. Sodium secretion does have an effect, so sodium levels does have an effect, and ACTH does have an effect, but the major effect is renin-angiotensin system or extracellular fluid volume and serum potassium levels. So renin-angiotensin system, we know that kidneys release renin, which is converted into angiotensin 2, which stimulates the aldosterone release. Plasma concentration of sodium and potassium directly influence the zona glomerulosa, especially the potassium levels. ACTH causes small increase of aldosterone during stress. Atrial natriuretic factor, which is a protein released from the heart. So when you have more extracellular fluid volume, your atria are going to be stretched. It is going to produce atrionatric peptide, which inhibits the activity of zona glomerulosa. Okay, we'll stop here before we start with the functions of the